solenoids, motors, stepper motors in the case of a idle controller, or servo or an actuator at very high speed. Throttle motors, for example, are pulse width modulated by an H bridge at sometimes greater than 30 kilohertz of frequency. That is an incredible amount of speed, 31,000 cycles per second, for that motor to be receiving signals and shuttling back and forth. In its basic form, pulse width modulation is created by using all of the components we covered on the last slide, and then it's going to charge and discharge an oscillation or tank circuit. What's going to happen then is the IC, based on the integrated chip, based on the logic coming in there, is going to control the width or the delivery of that power based on input and output signals and programming, obviously. And one thing we need to realize as we move on here is that your pulse width modulation is also utilized very heavily on sensor and communication lines, not just power loads. Okay, now the duty cycle control, okay, basically is defined as the on or off time as compared to 100% of the cycle. Now, sometimes there's some mix-ups between duty cycle and pulse width. Pulse width is simply the on time, okay? Duty cycle is defined as the on or off time as compared to 100% of the cycle. I'm going to show you exactly how to look at that and measure it on a scope in the next slide here. But the percentage of duty cycle on time in a ground control application is typically going to be interpreted as 100% equals on, whereas 0% or near zero would be power off. Okay, but the percentage of duty in power controlled circuits can be stated as the reverse, which can be confusing in some service information like Honda, where you'll have a power controlled circuit where 12% will be full on and 88% will be full off. So it's very important when you're diagnosing pulse width modulation, and let's say you're working on a Ford with a pulse width modulated fuel pump and it's commanding 20%. You need to know whether that's power controlled or ground controlled and how Ford is interpreting that in their service information before you go try to read it on a scope or verify that the signal you're getting out of that scanner is correct with a scope, right? So there is a distinction there with duty cycle, whether the high or the low dictates the zero in power control being on and near 100% being off. Little bit of checking there that needs to be done when we're using service information on the car just to make sure we got that right. Basically, both interpretations are utilized by the manufacturer in this case. And then, of course, if we move the thought process from duty cycle to pulse width is simply the measured on time of any given device that's modulated. Excuse me. Now, basically what we have on the slide here is just a representation of a 10% duty on cycle up here, a 50% duty on in the middle, and a 90% duty on, as you can see, with the 10% off here on the bottom. That's basically what the oscillator is going to range between, which is your 10% and 90%, typically. Okay, sometimes it's 88 and 12, sometimes it's, you know, a little more than that, 92 and 8, who knows, depends on whoever designed it. Okay, but what's really controlling that is the pre-programmed logic or feedback coming into the IC chip, which the TTL or the logic is controlling the output in our power control circuits. So the beautiful thing about this duty cycle measurement on a lab scope is we can easily confirm that the PCM is reporting the correct information to the scanner data PID. But more important than that, we're not just verifying the front end of the circuit, meaning the analog power portion, because remember, our digital signal is the power in this application, but we're also really verifying the logic behind it based on the condition, shape, and characteristics of the waveform. So that is a really nice thing when pulse width modulation is used for power control is that it's all in one. You're basically reading the control of the chip, the output, and the analog wires going to the load, all in one screen if we're looking at current and voltage and some different ways to look at this signal completely in one shot. Why is this important? Because think about this. It's important because if I can learn to do this with a scope and a scanner plugged into the OBD2 port and a scope measuring the actual circuit for these characteristics, I'm able to take sometimes 10, 15, or 20 page DTC charts or pinout charts or test plans, whatever you call them. Okay, so you print out a code chart for an FRP sensor on the top of a gas tank, all right, fuel or FTP, fuel tank pressure, right? And you have a 15 to 20 page pinpoint test given to you by the manufacturer to go figure that circuit out. You know what, guys, if we get used to using a scope on a pulse width modulated output device, such as this fuel pump we're talking about, or a fuel pressure sensor, we can actually see the characteristics of the actual circuit, output device, control, and computer all in one shot. What does that mean? Instead of disconnecting each wire and measuring between here and here with a simple voltmeter to say, does it have 5 volts, yes or no? We're taking that circuit apart in a lot of ways when we're following that DTC chart. Using this method to look at pulse width modulated circuits, we back probe the load in the output device and possibly back probe the PCM on the same wire for the purpose of voltage dropping, and we turn that circuit on, and there's 15 pages of diagnostic answers right on one screen. Guys, this is huge, okay? So looking at pulse width modulation on an oscilloscope is a relatively easy thing, and when you guys get your books from me, those of you that email me for the book, you'll see that this very slide that formula is in the book for you guys to reference. You'll want to, if you're not used to measuring pulse width yet, you'll want to practice this. It does require a little bit of math, okay, but it's simple math. And if it's not whole numbers and there's decimals in front of stuff, just like everyone else, I'm going to use my cell phone calculator to get the answer. But the beautiful thing is you're looking at the actual power and the actual logic signal here, and you get your answers using this method of measurement. Now, typically, when we're going to measure a pulse width of any kind on an oscilloscope, the first thing we need is one full cycle of the waveform. For those of you that have been lab scoping for a while, you know that one full cycle of the waveform is where the waveform starts and then repeats again. So in this case, if you'll follow my pen here, we're going to take our cursor right here, and we're going to measure this rising edge of the pulse width modulated on time switch. We're also going to grab one cycle exactly by getting it where it repeats again. Now, just for the purpose of measurement, it does not matter, guys, if you want to move that cursor over to this falling edge here and here, that's fine. You just have to be consistent, and that holds true for AC waveforms and DC waveforms when we're measuring frequency or pulse width modulation. One cycle, doesn't matter where on the waveform, you just need to be consistent. Now, if you look at the graphic, we've got a 71 millisecond full cycle here. And what we're going to do to get the actual number on the scope is we can set up a math channel if one exists. For example, Pico, some Snap-on, ATS. There's a few of the manufacturers out there whose scopes are configurable with math channels that can look at this duty cycle, okay? But when we want to do a physical measurement on it on a scope, we're going to take our full cycle, and then we're going to measure the parts of the whole. So the way I like to describe it in scope classes is we're going to measure the whole, and then we're going to measure the parts of the whole, and then we're going to do some math. So in this case, we want to measure the on cycle, right, which is going to be 7.1 milliseconds, okay, and then we're going to do the formula. Now, In this case, you're always going to take the smaller number and divide it by the larger number to come up with your percentage. So here we have a full cycle of 71 milliseconds, an on-time portion of 7.1 milliseconds. We divide the two and we come up with a 10% on-time duty. Now, the same thing can be done for 80, 20, 70, 30, 50, 50, doesn't matter. Same math applies and the same measurement. We're always going to have a smaller number than the whole. Okay, so no matter whether it's 7.1 or down here, we measured the 90% on version right here and portion, and we get 64 milliseconds. Still a smaller number than the 71. So we're going to simply do this math right here. 64 milliseconds divided by 71 milliseconds equals your 90% on time. So that is the down and dirty simple way to get the answer on your pulse width using an oscilloscope. Okay, now again, it does not matter, not for a minute, whether this measurement is used for signaling or power control, because in the case of power control, the signaling and the power are one and the same. So this measurement works no matter what kind of pulse width duty cycle you seek to measure in whichever kind of circuit you want to measure it at. Now, let's get the slide flipped here. Now, what we did, and I'm going to stop the slide here, or stop the presentation in about another 2 or 3 minutes just to check for questions, okay? But this next section coming up on flyback voltage was done here in my little humble DiagNation lab. That's obviously not the kitchen sink, but the man cave sink there. We set up a little bit of a lab there with a Tektronix scope, and you can see the board here. And what we've done is set up a pulse width modulated motor, which you can see here with a current loop. Okay, so we're measuring current. We're also measuring voltage, and we're controlling with this capacitor and with a resistor the actual speed of the pulse width modulation. Now, what was really interesting about this was we were studying diodes and their effect on flyback voltage. And when you see the next couple slides that were born out of this experiment, man, you can really easily see how pulse width modulated power control circuits can reflect back and destroy a driver very quickly. What we're doing in this case is we're driving this signal with an audio generator, an audio oscillator, and then we're changing the resistance on these little slide switches or round switches here to make the circuit run faster or slower. Really cool little experiment to set up. Now, here's how we constructed the circuit. Now, this is a basically a tank circuit. Whoops. Okay. Whoops again. All right. Now, this is basically a tank circuit that's going to drive an output device such as that ignition coil, that fuel pump, or that injector. Okay. Obviously, we have our 12 volts up here at the top. Okay. Whoops. That's not the top. Here's the top. All right. Now, the way that this circuit works and the way it gets its pulse width modulation control is in the primary side, or if you will, of the control. So over here, we have, if you want to talk transistor for a minute, we have a base, we have a collector, and we have an emitter. All right, now what's going to happen here is we've got resistors inside that PCM controlling this tank circuit for this fuel pump. So we've got a resisted voltage being represented here. And here we've got another resistor, which is basically a sampling resistor. What's going to happen is there is a capacitor down at the bottom of this circuit. These resistors are going to be dropping and rising voltage on this side of the capacitor based on the capacitor. When the voltage is exceeded for the level of the capacitor, it will switch or discharge and cycle the voltage. So if you want to picture this now, we have a cyclical voltage coming in here to the input pin of the logic chip. Now this may be coming from pre-programmed output to this chip, and we're going to see it comes through. It is then passed in to the device. Our pulse width modulation is now going to be turning this transistor on and off, okay? And as it does so, the current is allowed to flow through from the ground, okay, or from the voltage, depending on where this is configured, up through to run the motor. Now, here's the important part for not destroying the driver. And this is what we need to look for every time we see a driver failure on a PCM for a transistor, a coil, or a fuel pump driver. We need to watch for the activity of this